The information we're going to be covering this week is, I don't know, I think it's pretty fascinating. It's one of my favorite sections. Definitely has some good videos for you to look at that goes along with this section. Because as you can see, hopefully you have this form in front of you. This is on earthquakes and earthquake information. So yeah, I have lots of different things to show you and talk about. So let's get into it then. So capital letter A, this heading then are types of seismic waves. So we're going to get into the different wave types here. And I have pictures that kind of go along with this stuff. So number one, first type of waves are called primary waves, or P waves for short. These are the waves that go through the earth by causing rock particles, rocks, to move back and forth in the same direction as the wave energy. And what I use in my regular classroom for this is I break out this gigantic slinky, which is like super long and it's super thick. It kind of goes along with this picture down here. So normally I have one kid stand at one end of the slinky and we just lay it across the length of the floor basically. And I have pretty big classrooms. And I have another kid stand at the other end. And I tell the one kid at the one end that he's the earthquake. He's the epicenter of the earthquake. And that person has to demonstrate the different types of waves. So by pushing straight, by causing the slinky to go straight, everyone can see that wave energy moving down the slinky. And there is no side-to-side motion with this one. It's perfectly straight. That's the great example of number one here, which is the P wave then. The other wave then, which is the S wave or secondary wave. Secondary waves are waves that move through the earth by causing rock particles to move back and forth at right angles or perpendicular to the direction of wave. So that's this picture here basically that you're looking at. So basically the kid at the one end then causes some left to right motion as they're making the wave travel forward. And you can kind of see that it forms that S wave. You get that S-like action of wave energy then. And that's a pretty crooked line that I just drew. But that's a good indicator of the way S waves. So as you can see from these pictures at the bottom, when an earthquake happens, basically, P waves and S waves travel outward in all directions. And they travel throughout the whole world for the most part, although S waves, as you'll learn here shortly, cannot travel through liquids, but they do travel in all directions. Now, the third type of wave are the really dangerous ones. These are called the surface waves. Surface waves originate from the epicenter. They travel outward in an elliptical, E-L-L-I-P-T-I-C-A-L, elliptical motion. These are the waves, obviously, that make it to the surface, and they ripple outward from the surface. So obviously, if there's buildings or things like that that are found at the epicenter, that's not where you want to be because those are the things that are going to rock back and forth. And if they're not built to earthquake-proof standards, obviously, there's a chance that they could topple or fall and things like that. A good example of this one is if you ever throw a stone into a lake or a river and you get those rings, those concentric circles that ripple outward, that's very much like how the ground behaves for S waves during an earthquake. So down below, they kind of go along with these pictures. This is the focus. Focus is the point inside the Earth's interior, like you see in this picture here, where earthquake waves are produced. And that's the P wave and S wave. They come from the focus. I think I may have said epicenter before, but they're from the focus. And then the epicenter then is the point that's directly above the focus on the surface. So you look at this picture. Here's the focus. And then right above it is the epicenter. So a lot of times the epicenter isn't along the fault line that reaches the surface. It could be, this picture shows it being a short distance, but it could be a mile or two away. So that's why it's not always very accurate to predict where earthquakes are going to cause damage because the fault line may be in a totally different place in the city than what the epicenter or surface waves are. All right, so part B then is titled locating an epicenter. So how did the scientists do it? Well, what they've discovered over the years is that these seismic waves travel different speeds. P waves are the fastest. They travel fast. Because again, think about that motion that they have. They're traveling straight. They can move much faster. L waves are the surface waves. I should have told you that before. So P waves, the abbreviation's P. S wave, the abbreviation's S. And because S is already used, surface waves then are abbreviated L. They're also called the long waves or the longitudinal waves, so that's where the L comes into play, basically. Secondary waves then are somewhere in the middle. So when you look with this seismograph reading that's right here, basically a pen sits on top and it's moving along, not doing anything. All of a sudden it starts to go back and forth. Well, that's the arrival of the P wave. So you would mark down the time, whatever time that is, 10:30 or whatever. Then eventually you get the arrival of the S waves, which is this other wave that's here. And again, you would mark the arrival time. And then if you're close enough to the station, you would see the arrival of the secondary waves, which are the really big back and forth, side to side motion, basically. So one station uses the arrival of 3 waves to determine how far away an epicenter is. Unfortunately, just by having one seismograph station, that doesn't tell you direction, it just tells you how far away it is. So really, you need data from three stations to locate an actual epicenter then. That's called triangulation. If you know anything, maybe you've been a Boy Scout or a Girl Scout and they've done triangulation before, but that is how they would locate an epicenter then. All right, part C is titled Mapping Earth's Interior Using Seismic Waves. So how do we know exactly what the Earth is made up of inside? How do we know exactly how thick those layers are? Because really, we've only ever been as deep as like halfway through the crust, which is the first layer. Even drilling deep into the Earth, the deepest we've been is halfway through the crust. So how do we know about the mantle? How do we know about the outer core? How do we know about the inner core? Well, we study earthquake waves. What scientists have learned, number one, at certain depths, the speed and path of seismic waves change. Basically, P and S waves, when they hit the mantle, they speed up, they get really fast. So that's how scientists know when the crust stops and the mantle begins, basically. That boundary, which is number 2, it's got a really weird sounding name. It's called the MOHO discontinuity. It's 2 words. M-O-H-O is the first word, MOHO. Second word, discontinuity. D-I-S-C-O-N-T-I-N-U-I-T-Y. It marks the boundary then between the crust and mantle. Crust and mantle. Basically, that's the point where seismic waves, like I said, they speed up at that point. Another interesting thing for this example, as you look here where the earthquake is, P and S waves travel outward in all directions. But you'll notice that the S waves, they kind of stop here at this outer core. They can't travel through liquids, which is what we've learned over the years. This is kind of the answer number 3. It creates what's called a shadow zone. Shadow zone. It's an area on the Earth that's always between 105 to 140 degrees from the focus where no seismic waves are detected. So look, because the S waves hit this region right here and the P waves get bent, you get these areas that are always 105 to 140 degrees. Remember, a circle is 360 degrees. So it's always 105 to 140 degrees. This area here, it's called the shadow zone. And again, why is that? Well, S waves can't travel through liquids, and P waves slow down and get bent or deflected. So that's how we know a lot about Earth's insides, is because we look at the seismic waves then that come from them. All right, so there are a couple assignments with this section, obviously, and some other videos that you're going to take a look at. And if you have any questions about earthquake waves, I know this is a pretty interesting topic. You're more than welcome to email me this week, and hopefully I can find the answers or point you in the right direction for finding your answers.